I'm back as promised with a video on the behavior of conductors. Now we will be talking exclusively about metallic conductors and not about the electrolytic conductors. That's a chapter covered in chemistry. We will be covering in this video only metallic conductors and their behavior in what are called electrostatic conditions. Now what happens with metallic conductors is they have lots and lots of free electrons which are free to move, and if there is some applied electric field, these electrons will move, and therefore charges within the conductor will move, and therefore there is a capability of charges to be able to move within a conductor when the conditions are right for their movement. Now we will be also discussing exclusively conditions which are electrostatic. So we are studying the behavior of conductors in electrostatic conditions, and by that what we mean is that charges are at rest. So even though we're talking about conductors, we're talking about metals, we will be discussing conditions which are essentially electrostatic. So even though charges are there on the metal surface or the metal body somewhere, they are at rest. So to start with, very first point that we need to discuss here is that electric field inside a conductor is zero. Inside a conductor in electrostatic conditions, the electric field has to be zero, otherwise conditions cannot be electrostatic. And let me explain this. If we have a conducting object here, this is the conducting object, and if we assume that there is some electric field in it, then the free electrons in the conductor will be moving opposite to that electric field. So if we have this electric field, the free electrons in this conductor will be moving opposite to this field, and these electrons will be moving en masse, lots and lots of electrons moving to the left, and therefore charges inside the conductor would not be at rest. So in the presence of electrostatic fields inside conductors, electrostatic conditions are not possible, and therefore if conditions are electrostatic, the electric field inside a conductor must be zero. Now the next point here is that if charge is given to a conductor, it resides on its outermost surface. So if we give charge to a conductor, somehow the charge manages to move to the outermost surface of the conductor. So if we have this conductor here and we give it some charge, let's say we've given it an amount of charge that's equal to Q, and we wait for a small amount of time. Now that amount of time would typically be micro or milliseconds at most. In that very small amount of time, the charge spreads around the conductor and achieves stable equilibrium extremely quickly. Now charge achieves stable equilibrium and comes to rest. So we have what we call electrostatic conditions. Charges now are on the conductor are at rest, and we have to now figure out where those charges are. Now, to figure out where the charges are, what we do is we draw a Gaussian surface just inside the surface of the conductor. So we've drawn here a Gaussian surface which is just inside the surface of the conductor. Now, as far as this Gaussian surface is concerned, the electric field everywhere is zero. If electric field everywhere on this Gaussian surface is zero because it's inside the conductor, that's point number one. Electric field inside a conductor will be always zero. If the field is zero everywhere, the flux through this surface is zero, and if the flux through this surface is zero, then the enclosed charge inside it must also be zero. And if the charge inside the Gaussian surface is zero, where is all the charge that we gave to the conductor? It must be outside this Gaussian surface. And what is there outside the Gaussian surface? What is there outside the Gaussian surface is the surface of the conductor, and that is where the charge is now to be found. Let's assume it's positive, so this positive charge will have spread on the surface of the conductor. So, charge given to a conductor will tend to always reside on its outermost surface. The next point, if a conductor is placed in an external electric field, then charges are induced on its surface. Now, this is something we are aware of. In fact, the very first video on electrostatics, we discussed about induction of charges. So that happens in conductors, it happens also in insulators. For insulators, we'll of course be studying the mechanism later on. But in case of conductors, there is an induction of charges when they are placed in external fields. Now, the field due to induced charges is equal and opposite to that of the external field at any location inside the conductor. So if you consider absolutely any location inside a conductor, the electric field due to the induced charges will be exactly equal and opposite to the external field at that given location. So if we have this conductor here, I'm shading this to show that this is a solid body, and we place it in this external electric field, EE, let's say. And because of this, the electrons in the conductor move to the left, and since they eventually settle on this left surface of the conductor. And since we have a negative charge here, there must be an equal and opposite positive charge I'm making the assumption that the conductor was initially uncharged. So the conductor was initially uncharged, there was no charge on it, we place it in an electric field, and then charges get induced. Negative here, positive here. Now let's look at this location inside the conductor. Now at this location, the electric field due to the induced charges will be exactly equal and opposite to the electric field at that point because of this external field. So electric field due to the induced charges at any point inside the conductor will be equal to and opposite to the external electric field at the same point. So this is a kind of very, very important point, and often questions are framed based on this particular point. So please make sure you have this on your fingertips, that if a conductor is placed in an electric field, charges will be induced on its surface, and they will be induced in such a manner that at any point inside the conductor, electric field due to the induced charges will be exactly equal and opposite to the external field at that particular point. So that's something kind of very important here. Now we move on to the next point, and that says the electric field just outside the surface of a conductor is normal to the surface. Now why so? Now you see, we have already discovered that inside a conductor the electric field is zero, and since the electric field is zero, if you move from one point to another inside the conductor, since the electric field remains zero, the change in potential from here to here or from here to here will be zero. So the potential of a conductor is always same throughout. Since the potential is same throughout, the surface of the conductor is an equipotential surface, because surface of a conductor is an equipotential surface, and we are already aware from our earlier discussions that if you have an equipotential surface, electric fields will always be normal to an equipotential surface. So if we have say the surface of a conductor here, this is just a small part of the surface of a conductor, and it has some charge on it, then the electric field lines will be radiating normally outward from the surface. So just outside the surface of a conductor, electric field is normal to the surface, and the moment you move inside the conductor, the conducting body here, the electric field will be, net electric field will be zero. So that's the initial bit on the behavior of conductors. There are fair number of more points, and we'll move on to them now. The next point is actually about the magnitude of this electric field. Now consider this. Consider a small part of the surface of a large conductor. So this is a small surface, small part of the surface of a large conducting body. Now let's say it has a surface charge density sigma. Its surface charge density is sigma. Let's consider a tiny portion of this surface having a surface area dA. Let's say we have a small disc shaped area dA here. Now if you move very, very close to the surface of a disc, the disc itself produces a field equaling sigma by epsilon naught. So if you have this small disc having a charge sigma dA, that sigma dA will produce an electric field sigma by 2 epsilon naught. So of course the point needs to be very, very close to the disc for this to be true. Now we'll be considering 2 points, one just outside the conductor, one just inside the conductor, and we are dividing our universe into 2 parts. One part of the universe is this charge sigma dA, and then we have the rest of the universe. This part of the universe we'll call 1, and the rest of the universe we will call 2. So sigma dA charge we will call 1, and rest of the universe will be calling 2. So this sigma dA is 1, and the rest of the universe is 2. Now, just outside the conductor here, the electric field due to this sigma dA, and I am assuming this to be positive, the electric field E1 due to this sigma dA will be sigma by 2 epsilon naught, the field due to a small disk. Similarly, inside the conductor, the field due to this sigma dA, again I'll be calling it E1 because this part of the universe is being represented as 1. So the field here will be to the left, it's a positive charge, so field points away from it, and the magnitude of course is same. Now let's think of the electric field in this region because of the rest of the universe. Now in this region of space, the electric field because of the rest of the universe will be in this entire region, the electric field due to the rest of the universe is E2, and it must be equal to the magnitude of sigma by 2 epsilon naught. Now why should it be exactly sigma by 2 epsilon naught? Because the net electric field inside the conductor has to be 0, and therefore the field due to the rest of the universe has to cancel out the field due to sigma dA, that is 1. So just inside the conductor the net field becomes 0, and just outside the conductor, since both these are in the same direction, the net field just outside the conductor will be the sum of these two, and that's sigma by epsilon naught, and that's the net field just outside the surface of a conductor. Now there's another interesting conclusion that can be drawn from here. and that's about the pressure that this part of the conductor experiences. The amount of charge on this part of the conductor is sigma dA, right? The charge on this part of the conductor is sigma dA. Now, how much force in the outward direction will it experience? It will be an outward force. Mind you, if the charge here is positive, the field here is outward, and therefore the force is outward. If the charge here is negative, the field will be inward, and the force still ends up being outward. So it will always be an outward force whether the charge is positive or negative. So the outward force will be the amount of charge sigma dA times the electric field E2. Why E2 and why not E out or E1? Well, E1 is the electric field due to this charge itself, and no charge experiences a force because of its own electric field. So no charged particle, no small charge, experiences forces because of its own fields. This charge is experiencing a force because of the charges elsewhere in the universe, and therefore we are using E2. This is the field due to charges other than sigma dA. So this dF out equals sigma dA times sigma by 2 epsilon naught. Now what I do is I take this dA onto the left hand side and I get dF out by dA, and this equals sigma square by 2 epsilon naught. And since this is force per unit area, this is outward pressure. This is an outward pressure, also called electrostatic stress. So this outward pressure is also called electrostatic stress. Now, we have therefore calculated the electric field just outside the surface of a conductor. It will be sigma by epsilon naught, where sigma is the electric field in this on the surface. Inside the conductor, the net field has to be 0, and there has to be an outward pressure sigma square by 2 epsilon naught on the surface of a conductor. Now we move on and discuss another very interesting point. Let's say this was, I have lost count of the points, I think this was maybe 5, and so we're moving on to 6, and this says if a charge Q is kept in a cavity inside a conductor, a charge minus Q is induced on the inner surface of the cavity. Now see what's going on here. Let's say we have a conductor with a cavity here. This is the conducting material here. So we have a conductor with a cavity inside it. Now inside the cavity here, I have placed a charge plus Q. Now what this plus Q does is it attracts the negative charges within the conductor and they assemble on this inner surface. So a negative charge, if this charge is positive, a negative charge will be induced here. If this is negative, a positive charge will be induced here. Now if the conductor is initially uncharged, we have some negative charge here and therefore an equal and opposite positive charge on the outer surface. Now the point of interest is that this charge on the inner surface of the cavity has to be minus Q. Now why is that? Let's draw a Gaussian surface here. I've drawn this Gaussian surface, and on this Gaussian surface the electric field is zero everywhere because the Gaussian surface is inside the conductor. Therefore the electric field on the Gaussian surface is zero, and therefore the flux on the Gaussian surface is zero, and hence the enclosed net charge has to be zero. So the net charge inside the Gaussian surface is zero, and if the net charge is zero and this happens to be plus Q, then this has to be minus Q. And the point is therefore made. It is proven that if there's a charge Q inside a cavity in a conductor, a charge minus Q must be induced on the inner surface of the cavity. Now the next point here is about potentials. If two conductors are brought in contact, they exchange charges till their potentials become equal. So if you have two conductors and you bring them in contact, or you connect them by a wire like this here, we have two conductors, there's a wire connecting them. So if we had two conductors which were charged and then we connect them by wire, then they exchange charges till their potential becomes same throughout. Now why should the potential become same throughout? There's a very simple logic for this. Once you've connected them, they are no longer two different conductors, but they are both parts of one large conductor. And in a given conductor, the potential has to be same at all points within the conductor. So the potential everywhere within a conductor has to be same, and since it's now one conductor, the potentials have to be equal, and therefore charges have to be exchanged accordingly. And another very interesting offshoot from this point is that if a conductor is connected to the earth, the potential of the conductor becomes zero. Now it is arbitrarily assumed that the earth has the reference potential or zero potential. So if we have a conductor here and we connect it with the earth, this is the symbol for the earth connection. Now if we connect this conductor to the earth, the potential of the conductor must become zero. Now why is that? The potential of the earth is the reference potential, or zero, and if this conductor exchanges some charges with the earth being so gigantic, the potential of the earth does not change, so it remains zero, and therefore the potential of the conductor has to be adjusted to become equal to the potential of the earth, which then we know is zero. So when a conductor is connected to the earth, the potential of the conductor necessarily becomes zero. Certain books tend to say the charge on the conductor will become zero, but then that is not correct, not necessarily true, but potential becoming zero is necessarily true. So very, very important point, and we'll discuss this a little bit further now. In a very important example also, we'll be highlighting another very important property of conductors called corona discharge there. So what we'll be considering is, we'll be considering two conductors, spherical ones, because with spherical conductors we can easily calculate potentials and fields. So we have two spherical conductors having radii A and B. We also assume that the distance between them is very, very large, and let's say this conductor on the left carries a charge Q, and this is initially uncharged. Now what we do is we connect them via a wire. Let's say the wire has a switch here, and we connect the switch, and when the switch is connected there is an exchange of charges. Eventually the charge here becomes Q1 and the charge here becomes Q2. Obviously, using conservation of charges, Q1 plus Q2 has to remain equal to capital Q, and that's our conservation of charges, call it equation 1. Also the potentials must become equal, and I have assumed that they are fairly far apart, so the charge on one conductor does not produce any potential here. So charge on this conductor is not producing a potential here. The charge on this conductor is not producing a potential here. So this potential is 1 by 4 pi epsilon naught Q2 by A is equal to the potential here 1 by 4 pi epsilon naught Q1 by B. Now this 4 pi epsilon naught cancels, and therefore Q1 by Q2 equals I think I've messed these two up. Q1 by, let's say Q, we have Q1 here and Q2 here, and we'll be writing things accordingly here. Q1 by A and Q2 by A, and eventually now we have Q1 by Q2 equal to A by B. Let's call this 2. So what we're noticing is charges are directly proportional to the radii. So you can even calculate Q1 and Q2. Q1 will come out, if you solve these two equations, Q times A by A plus B, and Q2 will be capital Q B by A plus B. Now since charges are proportional to the radii, let's say Q1 is proportional to A. Now the sigma surface charge density sigma 1 will be proportional to, now charge is proportional to A, the radius. Now you divide by the area, 4 pi A square. So you divide this by 4 pi A square, you end up with 1 by A. So sigma will be proportional inversely to the radius. So sigma 1 is inversely proportional to A and sigma 2 is inversely proportional to B. Now this has interesting consequences. If, for example, we have a large conductor with a pointed corner here, now some pretty interesting things can happen. Let's say we have given an amount of charge Q to this conductor. So we have given a charge Q here, and this charge Q is then distributed on the surface. Obviously it distributes according to this rule. Sigma is inversely proportional to A. So the surface charge density over these areas will be relatively less, but at this sharp corner here, sigma will be highest. Let's say this point is A and this is B and this is C. Then sigma at A will be greater than sigma at B, which has a small radius, but then C is a fairly flat surface. It has a large radius, so sigma at C will be least among the 3 points we have considered. So sigma at A will be maximum, followed by sigma at B and followed by sigma at C. At A there is a very sharp pointed corner, which means the radius of the surface is very tiny. This is also somewhat pointed, and therefore the radius is relatively small here as well. But of course at A the radius was least, followed by B. At B the radius is more than A, but at C the radius of curvature will be maximum. And surface charge densities are inversely proportional to radii, and therefore sigma at A will be greater than sigma at B, greater than sigma at C. Now the electric field over here, E at A, will be greatest of all the among all the points here. So at A we have a very large electric field, and because the electric field here has become very large, something very interesting happens. Normally the air outside is an insulator, but when you apply a sufficiently large electric field, even a dielectric can become a conductor, because with very large electric fields, electrons are ripped off from the molecules, ionizing them, and therefore now you have an availability of positive ions and negatively charged electrons in this region of space. And since you have negative electrons and positive ions available, this air can start conducting. Now remember that outward pressure that charges experience, and here because sigma is very large, there is a very large outward pressure as well, and the air outside is now conducting. As a result, what happens is this body starts spraying charge. So there's a spray of charge in the form of sparks. So we can see sparks flying and charge leaking out of the body. This discharge from sharp edges is called corona discharge. This type of discharge is called corona discharge, and this corona discharge happens when electric field in the region exceeds what is called the dielectric breakdown strength of this air. Now, in fact, every dielectric material, including air, has something called dielectric breakdown strength. Now, this dielectric breakdown strength is the minimum magnitude of electric field which causes a breakdown of the dielectric, making it conducting. So every dielectric has its own magnitude of this quantity. It varies from material to material but is typically constant for a given material. Since air too has a breakdown strength, it starts conducting, resulting in what we have just named the corona discharge. Now there's more to conductors, so a couple more points here and then we will be done. Now the next point about conductors is regarding what's called the electrostatic shielding. This is another very interesting concept related with conductors. Now let's see what is electrostatic shielding. And by now I have thoroughly lost count of how many points there have been, so I guess you can count them yourself and note this down. So electrostatic shielding. What's that? Consider a conductor here with a cavity inside. So this is a conductor with a cavity inside. Now this first point in electrostatic shielding says field in an uncharged cavity in a conductor is 0. Now why is that? Now let's say that there are electric fields outside the conductor and initially the conductor has no cavity. And if the conductor has no cavity, the electric field in this space is 0 everywhere. And the material inside also is electrically neutral. There is no net charge on the material because any net charge would reside on the outer surface here. Now what we do is, even though there are external electric fields, we are aware that there are no fields inside and there are no charges inside. Now somehow, using whatever technology we can, we scoop out this material. We kind of put in a syringe, ensure that some material melts and we suck it out. So we end up having a cavity here. Now in this cavity the material has been removed. Now the material that was removed was electrically neutral, and when you shift electrically neutral material, there are no changes in electric field anywhere in the universe. The field here was 0 earlier and it remains 0 now. So the field will remain 0 even after the removal of this material because the material was electrically neutral. And when we shift electrically neutral materials, there are no changes in field. So that's the first point in electrostatic shielding. Now the next is just as interesting. We have a conductor with a cavity inside. So we have this conductor, it has a cavity here, and we keep a charge in here, let's say plus Q. So there are negative charges induced on the inner surface of the cavity and positive charges on the outer surface. If this is plus Q, this charge on the inner surface is minus Q, and any electric field lines that originate here terminate on the inner surface of the cavity. Now even if I shift this charge from here to, let's say, this point, these field lines that start off from this charge will meet the same fate. They will still come and terminate on this surface, and as a result, a shifting of this charge means there is no change in the space outside this surface. If there is no change in the space outside this surface, because no field lines come out of it, there are no changes in electric field in the region outside this conductor. So as you shift this charge, the inner surface of the cavity has a readjustment of charges, but field lines still terminate here, and no changes happen outside because these charges do not shift, because there is no electric field line moving out of this space, essentially meaning no electric field coming out of this space, causing a rearrangement of these charges. So these charges remain where they are, there is no rearrangement, and therefore the electric fields outside do not change. So a rearrangement of charges in a cavity inside a conductor does not alter the electric field outside the conductor. Now interestingly, even the converse of this is true. The converse of this is true as well. If we rearrange charges outside the conductor, electric fields in the cavity inside the conductor will not change, because if you have a charge outside, all its field lines will terminate on the outer surface, never entering the conductor. So not only this statement, but its converse is true as well, and I'll write that converse down here. A rearrangement of charges outside a conductor cannot alter the electric field in a cavity inside the conductor. So this set of points, this set of 3 points, is what we call electrostatic shielding, and this concludes this video on the behavior of conductors. Very interesting concepts, very exciting concepts, which we've now completed, and we'll be applying them in some interesting applications in the next video. We will also be introducing the concept of capacitor and capacitance in our next video. So exciting times ahead, very interesting topics, great amount of fun to be had. Please stay tuned into this channel, like, share, and also do subscribe. Thank you very much for continuing to support the channel. Thanks a lot.